So today, today's experiment is about solution and about calculation solutions and the calculations of the solutions molarities and other type of concentration calculation like mass over mass, mass over volume, percentage. So if I want to share with you the file of the experiment, here it is. And the solution is made of a solute, which is a small amount, and a solvent, which is an extra amount, in large amount. So that's the ratio of the volume of each solute to solvent. So a solution is always defined as homogeneous mixture. You can't have a solution that's heterogeneous. It has to be homogeneous mixture. That's a must. That's a condition. It has to be met first before you start talking about solution. That's what brings us to the first part of the experiment, which is like dissolves like. Like dissolves like. If the solute is polar, in order to have a homogeneous solution, you have to have the solvent has to be polar and vice versa. If the solute is non-polar, then the solvent has to be non-polar as such. So they have to have the same polarity. Solvent and solute, they have to have the same polarity, because that's will get you to obtain a homogeneous mixture. If they have different polarity, then you don't expect they will have homogeneous. They will have heterogeneous mixture, and that's what the first part of the experiment. So the first part of the experiment here, as you can see, we can do those together here. We have two solvents. One is a polar solvent, H2O, correct? And this is let me just this is H2O. First of all, it is our circle, the H2O here. That's our solvent here. H2O is polar solvent, and it is polar. Okay, and then you have different. We'll test those this solubility of this solvent in different compounds. Those compounds or solutes, they can be polar or non-polar, and you will see in order to have a solution, you have in H2O, which is polar, you have to have a solute, or this compound has to be polar. So we have potassium nitrate, we have iodine, we have potassium permanganate, we have sugar, we have oil. Five compounds. Again, repeating myself. We have iodine. We have we'll look at iodine if it's polar or non-polar. And we have oil. You have potassium nitrate, correct? And you have potassium permanganate, and you have sugar, the kitchen sugar. So let's look at this. This is the polar solvent, and let me just show you here. Take it out. So here it is. Those are the five. So the five components here. So first of all, with potassium nitrate, this is potassium nitrate. Now, tell me what you know about potassium nitrate. It is polar or non-polar? What do you think? Potassium nitrate is polar or non-polar, and why? Come on, guys, that will be maybe in your lecture final exam. What type of potassium nitrate? What type of bonding there in potassium nitrate? Yes. Non-polar? No, that's not correct. Then you'll tell me it's polar because the other side, yeah. Now I wanted to know what type of bonding in potassium nitrate. My goodness, don't let me down here. That is ionic bonding. All ionic bondings we decided to be polar, correct? Ionic bonding are polar. So you have potassium cation positive, and you have the anion. This is anion, negative, polyatomic anion. Right, guys? So you have potassium nitrate. This is ionic. So this is polar, and the H2O is polar. So is solution formed? Yes or no? Yes. So predict, will a solution form? Yes. Because the fact that potassium nitrate is ionic, correct? Potassium nitrate is ionic, and it is polar. Okay, so we filled the first compound. So we will have a solution made of potassium nitrate and H2O. Like dissolves like. H2O is a solvent polar, and potassium nitrate is ionic and polar. So polar makes what? Homogeneous mixture, and that's the solution itself. So we'll go to the second one. We have iodine. Iodine is polar. This is the Lewis structure of iodine. So it is, you have seven of those here. Seven valence electrons. Okay, so you have seven electrons here. So is iodine polar or non-polar? Non-polar, why? Polar, why? Tell me what. Covalent, why? Covalent what? Covalent bond, there's H2O is a covalent bond, but it's polar. How we can determine it's polar or non-polar? Come on, guys, you did cover this one here in the lecture. Those are with me in the lecture part, cover that. So how we determine that's the covalent bond being polar or non-polar, or any bond? Don't let me down, guys. How? We forgot about this? No, not this. What really determines the polarity of a molecule? I told you to memorize for the final exam the table. Did I tell you now you can use it? Open book, you can use it, but in the final exam you can't use it, correct? So let's go look at this. Here, let me just switch color so you will not be, let me down here again. So 0 to 0.4, that's electronegativity different. Electronegativity, En means electronegativity, and delta means different. Electronegativity difference. From 0 to 0.4, then we have covalent, yes, but non-polar. Non-polar. Greater than 0.04, that's the difference between what? The atoms, the non-metal atoms that are making the bond, correct? Greater than 0.4 to 0.8 or 0.19. This is covalent, what we call it? Polar, correct? Greater than 1.8 or 1.9, this is ionic. That's we can determine the polarity of any compound, whether ionic or covalent. Are you following me here? Everyone's following? That's you have. Whoever is in my lecture, I know you are here, a couple of you in my, we covered that, correct? We covered that. So if I have the difference of electronegativity, and there's a table there, feel free to use it. And the final exam, I told you cannot use it because those values will be of electronegativity will be given to you. What's the highest electronegative element in the periodic table? Remember that? Fluorine atom, correct. What's the lowest one? Cesium, francium is 0.7, cesium 0.7. Yeah, so this is the table here you have to use. Now, iodine, I don't know the number, but this is the same. You make the difference between the same atom, correct? Same atom, two of them. You make the difference with them. The difference will be what? 0, correct? The difference between them will be 0. Whatever the value is, 2.0 minus 2.0 is 0. Same, identical. That's what we have said before about whisper. If you have the same terminal, identical terminal, then the molecule will be non-polar. It's the same idea, because even if you get it through the table, this is 0 difference of electronegativity. So then this is iodine is covalent non-polar. H2O is polar. So are we making what? Are we making homogeneous or heterogeneous? We are making heterogeneous solution because solution is not iodine is not soluble in H2O. So let me take this one out. Can I take this one out and answer the question here? Okay, so with iodine, the answer is no. We are not predicting that will happen. And is solution formed? No solution. Okay, guys. So let's look. We did potassium nitrate, we did iodine, and then we'll go and look at the demo here. And then how about H2O and oil? Oil is non-polar, correct? It's not soluble in H2O, correct? So therefore, no and no. Because oil is non-polar. Oil is non-polar. So we are dealing with the solute is non-polar. So it will be no. How about sugar? Sugar is in H2O. Is soluble? Yes. They are polar. Sugar is polar because the difference between carbon and oxygen, if you look at this is sugar here. If you look at the sucrose, if you look at the sucrose here, that's a sugar, kitchen sugar. You have a difference between oxygen and carbon all over the molecule, correct? So electronegativity is not 0, it's not 0.4, it's greater than 0.4. So you can look at that. So carbon is 2.0 and oxygen is 3.5, so it's about 1.5. This is covalent polar. So therefore the answer here, yes. The answer is yes. How about the last one, permanganate? Permanganate is what type of bonding in permanganate? Covalent or ionic bonding? And what's type of bonding in sugar? What's type in iodine? We know that's covalent bonding. How about sugar and potassium permanganate? What's the bonding we have here? Come on, guys. So ionic where? Which one ionic? Potassium permanganate is ionic. Why? We have a metal here. We have two metals. We have potassium and we have manganese. So we have potassium and manganese. Manganese in this one has charge of 7 plus, 7 plus. So this one here, potassium permanganate, is ionic, polar, correct? So we can expect with H2O will form a solution and will be soluble. How about covalent, the sugar, the kitchen sugar, and the oil? What type of bonding? What type of bonding? Both of them are covalent. The oils can be hydrocarbons. They are unsaturated. Okay, unsaturated fatty acids. Okay, so it's unsaturated, and they have a double bond, but they are non-polar. They are non-polar. So now we have. Just look at this. Can I take this one here? So now we have potassium. I'll just make a summary of this so you can follow me here. Summary of this. Will solution form for potassium nitrate? Yes. Will is a solution formed? Yes. With the oil? No. Is a solution with the oil? No. Is something soluble? No. Iodine? No. No. Sugar? Yes. Yes, you expect the solution will form and express solubility. And this is yes. Whoops. This is yes. This is yes. 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 And yes. Yes. So that's answers. That the whole thing answers the first part. When your solvent is what is polar. When the solvent is H2O, that's our solvent here, is polar. Okay, guys. So that's what it says. Okay. Y for yes and N for no, just abbreviation. So now we'll have see get this. We'll see first of all we see potassium nitrate. Potassium nitrate. So guys, can you see this one here? That's a H2O by itself. This is H2O by itself. It says that's a reference. You see pure H2O. Now we'll have potassium nitrate in H2O. We'll have our potassium nitrate in okay, so this is potassium nitrate in H2O, and this is your reference pure H2O. So this is H2O. This is the right one. This is H2O pure solvent, and this is potassium nitrate. Can you see it? This is potassium nitrate. It's very pure, very nicely. It's homogeneous mixture. You don't see two layers. You see one single layer. Okay. So this one is here. Second one, we'll have see the sugar then, or we see what the oil. So let's see the oil here. Here we are. That's the oil here. What you can see, that's the pure H2O. That's a pure H2O on it. See here, what you can see, what you can tell me. You can see two layers, and they separate according to the density. Oil is less dense, it will float on the top of H2O layer. So we have two layers. So not homogeneous. Homogeneous mixture, as you saw it in potassium permanganate, one single layer. This one here you have two layers. So in the back you can see it, two layers. So now we take the iodine. Iodine might be not obvious, but it is this iodine H2O. This is your H2O. This is your reference. solvent, the polar. This is your iodine. Don't worry about the yellowish stuff. Iodine is the bottom. See the bottom crystals? It's not soluble. Don't worry about this. This is just coloring from the solution, but it's not soluble. Iodine is non-polar. So you see here the crystals. Can you see the crystals? So it's not soluble. So this is a heterogeneous mixture. So then we have the kitchen sugar, sucrose. Sucrose. Can you see this is the pure H2O. This is pure H2O. One single that's solvent, one single layer, and this is sugar on the top. See here says sugar on the top. See here, all the sugar. You don't see anything at the bottom. Okay, that sugar is not soluble. So you can see here one single step here. This is the last one is potassium permanganate. Well, this is very hard to see, but believe it or not, potassium permanganate is purple crystals, and they are ionic and they are soluble in H2O. But you can't see because they always will give you a coloring because they have a unique color, very dark purple color. So, but the main thing is, in order to see this, you don't see any crystal at the bottom. See, it's highly soluble in H2O. See here. And this is a very strong oxidizing agent. So if you get it on your clothing, you can kiss your clothing goodbye. So it's very, very, it's more than even Clorox. Clorox is very hypochlorite and hypochlorite and chloride, not aggressive like potassium permanganate. Potassium permanganate is a very strong oxidizing agent than the Clorox itself. And it does stain, and the stain is meaning you cannot take it out. You have to cut your clothing around this stain. So, but this is ionic and this is soluble crystals, the very dark purple crystals. So those are the demo for solubility. Right? And solutions with the polar H2O, and we could not make solutions with H2O with iodine and oil. Those are non-polar. Those two things. No means oil and correct. So oil, we cannot make solution, and with the iodine we cannot make solution because they are non-polar. Correct? Because they are non-polar here, both of them. So let's look. Any question you have? Any question you have? Cyclohexane. So we have now. So any question about this? Let's look at the, we'll have another system. Here now the solvent is non-polar. Cyclohexane is non-polar. So we have cyclohexane here is non-polar. Correct? So cyclohexane looks like this. Cyclohexane is well, I'm not to write on this. But cyclohexane looks like this, guys, here. It does not want to write. I don't know why. So maybe thicker one is much better. So it means you have carbon connected to carbon, connected to carbon, connected to carbon, 6 carbons. 1, 2, 3, 4, 5, 6. And the rest is hydrogens. So this is what this is non-polar. Cyclohexane is non-polar. So that's what we have here, being what? Non-polar. So what our expectation is, if the solvent is non-polar, and like dissolves like, then we are expecting the non-polar iodine and the non-polar oil will be soluble in what? In cyclohexane. But cyclohexane will never be able to dissolve the sugar, the potassium permanganate, the potassium nitrate, right? So that will be no solution. So our expectation, can I take this one out? Okay, I'm taking this one out. Our expectation from whatever we have seen here, the first part, potassium nitrate is what? Polar. Polar. This is non-polar. So potassium nitrate is polar, but the cyclohexane non-polar. So will be a solution form? No. So it will be answer is no. No. Oil is non-polar and cyclohexane non-polar. Non-polar dissolves non-polar. So this is yes. And this is yes. This is iodine is non-polar. Cyclohexane non-polar. Yes. Yes. Oops, sorry. Yes. Okay, so sugar is polar and cyclohexane non-polar. So no. No. Permanganate ionic polar, cyclohexane non-polar. And here non-polar, polars, no. So no and no. So you have 3 no's and wow and 2 yes. The other side is you have 3 yes and 2 no's, and here 2 yes and 3 no's. Okay, guys. So let's look at an example here. This is, we'll take the cyclohexane as a reference here. We have first potassium nitrate, potassium nitrate, yeah, that's cyclohexane. It's colorless, but it shows purple. But somebody has put the potassium with potassium permanganate here. So this is, so it has to be colorless. So that's cyclohexane. Now we put cyclohexane and potassium nitrate. You can see the cyclohexane is evaporated and the nitrate is still there. There's no solubility whatsoever. So you keep it not cyclohexane at the top, will evaporate per time, and you get your potassium nitrate at the bottom. It's not soluble. So with oil and iodine, this is totally different. See? Remember? See the cyclohexane with the oil? You see only one single non-polar, they dissolve each other. So cyclohexane is non-polar, and the iodine, and the oil is non-polar. So they are making one homogeneous mixture. So this is a solution. So we'll take with the sugar. See here, cyclohexane evaporated, and the sugar remains. So that's not soluble. It remains there. And the last one, potassium permanganate. Here it is. Potassium permanganate. You see it at the bottom. Cyclohexane evaporates. So all this solid at the bottom. So And the last one here with iodine, cyclohexane with iodine. This is cyclohexane with iodine. Here it is. Here it is. They don't have that cyclohexane with iodine. All the iodine is gone, and you don't see any crystals at the bottom. You can't see crystals of the iodine. They are soluble in cyclohexane. So again, the conclusion of this is like dissolves. Like if you have a polar solvent, will dissolve a polar solute, and vice versa. If you have a non-polar solvent, will dissolve non-polar solute. So that's the whole thing about the first part. And I take now the second part will take from you like last week, stoichiometry of solution. So let me take this one out. And here it is. What will happen here? We'll have a mixture of sodium chloride. We know that's what that there. It's like you for you, this is an unknown. You don't know the molarity of it. So today you will have to determine the molarity of an unknown, for us known, but for you that's an unknown solution. Homogeneous mixture of sodium chloride, kitchen salt, and H2O. So we have a solution here. This solution here is made of sodium chloride, NaCl plus H2O. This is H2O is your solvent, and this is your solute. So what we have to do, as you see the picture here, before start doing anything here, you have to measure with the graduate cylinder, correct? A 10 ml solution of this sodium chloride solution. You don't know the molarity. You have to determine the molarity of this solution. So take 10 mLs. Okay, you measure it with the graduate cylinder, and you have to record the precise volume from the graduate cylinder. Okay, guys. So you know that the milliliters of that, 10 milliliters. So then you will take a crucible here. That's a evaporating dish. This is the evaporating dish. And there is a watch glass. Need the watch glass to prevent, and then when you heat, you don't lose some of the crystals out. So what will happen here, you will have to weigh this watch glass with the crucible, empty, nothing inside them, both of them. So you have measured the 10 mLs in the graduate cylinder of the solution. Then you'll have to weigh both this system here, evaporating dish, and the watch glass. Try to take the evaporating dish that has, depth inside, not at the surface, but it goes in, so it will hold the solution for longer time for heating. Correct. So you weigh this one empty. That's the second step. The first step, we measure the solution, 10 mLs of solution using graduate cylinder. Second, we weigh the watch glass and the evaporating dish empty. Third, you take the 10 mLs you have just measured and you dump it inside the evaporating dish. So you put the 10 mLs inside. You go and weigh the whole thing. You got the 10 ml sodium chloride solution plus watch glass plus evaporating dish. Okay, guys, weigh them together. Now, the difference of this empty empty system, watch glass and evaporating dish. And this one is filled, correct? Filled with what? With the 10 mLs, correct? Solution of sodium chloride. The difference will give us what? Somebody will tell me? Will give me the mass of the 10 mL solution, correct? Will give me the mass. That's I need to know this. So this is this is the beginning before doing anything. Yes. Any question? So first the evaporating dish and the watch glass empty. Then you dump the 10 mLs inside. You weigh them all together. And then you make the difference. That will give you the amount in grams of your 10 mL solution, correct? So then you will set up your Bunsen burner system as shown here. You need an O-ring. You need to put then the evaporating dish with the 10 mLs and the watch glass in the top. Try to get this a little bit of opening for the watch glass so that some of the H2O will evaporate eventually out of the system. So, and I will say don't overboil because then it will break. The watch glass will be broken and the evaporating dish might crack. So avoid this. Well, I'll show you. I'll turn on the Bunsen burner for you. So then make sure that you stay there. Keep heating until everything is dry. You'll see there will be some condensation of H2O inside the watch glass. Keep heating it until all the condensation is out. Until all the condensation is out. Then when you are done, take the watch glass. You take the watch glass down slowly. Okay. Don't lose anything. There's some crystal in the watch glass. Try to scrape it inside the evaporating dish. Get both of them now with the white crystals. That's your sodium chloride. No H2O solution. No H2O inside the solution. Now you have just the salt, kitchen salt, white crystals. Pull it down and you go to weigh it with the watch glass, both of them. You will weigh now the watch glass, the evaporating dish, and the white crystals, all of them together. Okay, guys? Now you will have not the ml, so you'll go from there after heating to dryness. After heating to dryness here. After heating, you get evaporating dish. Evaporating dish plus watch glass plus sodium chloride crystals. Sodium chloride crystals. So everyone's following here? And that's it. You stop and then you do your calculation. If I know after the heating here, okay, watch glass, evaporating dish, and crystals, sodium chloride, I know what I have started with, correct? Empty. I subtract this, the crystals inside, with the empty one, it's gone. With the empty one, I get the mass of the crystals. Using the molar mass, I can determine the number of moles of this crystal, sodium chloride. Okay, I have 10 mLs. To convert the 10 mLs into liters, then I can divide, and this is here. All the steps are here. I put this one here for you guys. All the steps are here. So after you are done, you can calculate even mass to mass, and then you can calculate moles per liter molarity of your unknown solution of sodium chloride. How much sodium chloride? What's the molarity of it to begin with? Okay, guys. So all the steps are here to calculate with all details, step by step. So that's the whole thing. We have to determine the molarity of unknown solution made of sodium chloride. That's all. Any question before I close the WebEx, the recording? Any question? Okay, I will just close the recording.